The following video is on antiderivatives. We will be looking at the following question. If f prime of x equals x, what was f of x? Let's start with looking at this problem by looking at the power rule that we've learned when we learned derivatives. We know that f of x equals x to the n implies that f prime of x equals n times x to the n minus 1. The first thing that we did to get this was to multiply the function by its exponent, and the second step was to subtract 1 from the exponent. So if we want to go backwards, starting with f prime of x equals x to the n, we're going to reverse this process. Instead of subtracting 1 from the exponent as our second step, our first step will be adding 1 to the exponent. And instead of multiplying by the exponent as our first step, our second step will be divide by the new exponent. So notice that we're just reversing the steps that we did in the power rule, and we're doing the opposite operation. So subtraction becomes addition, and multiplication becomes division. So if f prime of x equals x, notice that first we add 1 to the exponent, so we get an x squared, and we divide by 2. We can check that this actually works by taking the derivative of f. When we do so, we get f prime of x equals 2x over 2, which comes out to x. Let's try some other problems. So if f prime of x equals the square root of x, remember that's the same thing as x to the 1/2. So we add 1 to the exponent, we'll get x to the 3/2 divided by 3/2. So that's our antiderivative. We can simplify this to 2 times x to the 3/2 over 3. Let's look at f prime of x equals 5x to the pi. Instead of first bringing the pi down, the first thing that I'll do is add 1 to the exponent. And the last thing I'll do is divide by pi plus 1. That's the new exponent. So I get 5 times x to the pi plus 1 divided by pi plus 1. Let's look at f prime of x equals 3x squared minus 10x. I'm going to take this term by term using the sum rule. So the first term I get 3x to the third divided by 3. And in the second term I'll get a minus 10x squared divided by 2. When we simplify, we'll get x cubed minus 5x squared. Let's try one more. F prime of x equals 1 over x to the 4. Remember, this is the same thing as x to the negative 4. So we add 1 to the exponent, which will give me x to the negative 3, and divide by that new exponent. So divide by negative 3. We will say that a function capital F of x is an antiderivative of little f of x if capital F prime of x equals little f of x for all x. For example, little f of x equals x cubed minus 5. So to find the antiderivative, that's the process that we were doing on the previous slide, we add 1 to the exponent and divide by the new exponent. So we'll end up with x to the 4 over 4 minus 5x. Notice that instead I could have ended up with capital F of x equaling x to the 4 over 4 minus 5x plus 1, because when I take the derivative of this capital F, I still get the little f that we started with. Or I could have rewritten this as capital F of x equals x to the 4 over 4 minus 5x plus pi. Once again, since pi is a constant, the derivative of this capital F is the same as the little f. Or, in general, I could write f of x equals x to the 4 over 4 minus 5x plus c, where c is any constant. This is called the general antiderivative of little f. C is called the constant of integration. We will say that a differential equation in x and y is any equation involving x, y, and derivatives of y. So for example, y prime equals x squared plus 1, or x times y prime equals 3x minus sine y. A solution to a differential equation is just the function y equals f of x that satisfies the equation. You might remember from algebra that you were asked to solve equations, and normally that means solving for x, such that you can plug in x to both sides and they end up being equal. This is the same idea, but here we're solving for y, and we're going to plug derivatives of y and y itself into both sides and hope that they're equal. For example, let's show that y equals 1/2 times e to the x plus c times e to the negative x is a solution to the differential equation y prime plus y equals e to the x. We first need to find the derivative of y, which we know the derivative of 1/2 e to the x is 1/2 e to the x, and the derivative of c times e to the negative x is negative c times e to the negative x. That's using the chain rule. So now I can plug that in for y prime, and I can plug in y equals 1/2 e to the x plus c times e to the negative x for y. When I do this, we notice that the c times e to the negative x's cancel, and I'm left with 1/2 e to the x plus 1/2 e to the x, which is e to the x. And that's exactly what we wanted. It turns out that it's actually very difficult to solve many differential equations. There are many courses that you can take on solving differential equations. We only offer one of them here at CSUMB, but we highly recommend that if you're interested, you talk to your professor about taking it. Let's look at the following differential equation. So y prime equals 2x. When we ask to solve this differential equation, we're asking for you to find the value y such that it's a function of x and it satisfies both sides of the equation. So we want to take the antiderivative of both sides. If I take the antiderivative of y prime, I'll end up with just y. And if I take the antiderivative of 2x, remember we want the most general antiderivative, I'll end up with 2x squared over 2 plus c. This simplifies to just x squared plus c. So the solution to this differential equation is y equals x squared plus c. We can check that this works by taking the derivative of y, which we know is 2x, plugging it in for y prime, and making sure that it equals the other side of the equation, which it does. This is called the general solution when we have the plus c. But we don't always need to have a general solution. Notice that y equals x squared is a parabola, and c is going to shift the parabola up or down. So depending on what c is, our parabola will be shifted along the y-axis. Let's say that we knew that the solution of our differential equation passes through the point 3, 5. So then we would plug into our solution. Y is 5 and x is 3. And when I do that, I end up with c is -1. That means that the particular solution in this case is y equals 2x minus 1. So this is the solution to the differential equation that also has a curve that passes through the point 3, 5. We want to talk about differential equations for a bit this semester, so we need some notation to be able to talk about them. If dy by dx is equal to f of x, and capital F prime of x equals f of x, then y equals we've written this weird elongated s here, we're going to read that as the integral of little f of x dx. So that's the same thing as saying that equals capital F of x plus c, so the antiderivative. We read this as the integral of little f of x dx equals capital F of x plus c. We'll explain the notation a little bit more as we move through Riemann sums. For now, we're just going to call this the integral symbol, and we're going to write it as an elongated s. For example, if I asked you to solve the integral of x cubed dx, what we're asking for is the antiderivative of x cubed. We know that that's going to be x to the 4 over 4 plus c, so that's our answer. Remember that this is just the antiderivative of x cubed. If I asked for the integral of cosine x dx, this is sine x plus c, and once again, sine x plus c is just the antiderivative of cosine x. If I take the derivative of sine x plus c, I end up with cosine x.